Hi, everybody. My name is Anthony Kramer, and today I'm going to be creating a parametric Christmas tree with structural analysis using Rhino, Grasshopper, and a plugin called Fenix. So, how do we make a Christmas tree? Let's start with its shape. First, we're going to create a cone. Now, this cone has a few simple inputs, one being the base plane, which is the center, and the plane which it's projecting from, the radius, and the length. We're going to put our model in inches so we can think of the height and width in terms of inches. For this, I'm going to add a couple of sliders. They're going to show up to 1,000 in both directions. Now that's a pretty big cone. So what I'd like to do is I'm going to just adjust it down so it's mostly shaped like a Christmas tree. Now, right now we have a cone, just a simple surface, an untrimmed surface. And what we'd like to do is get a mesh for that. So one way we can do that is, since we have a surface, we're going to do mesh surface. This is going to take the surface as an input, and then it's going to take two parameters for the U and V directions of the mesh. And here we can put a couple of sliders again. So go up to 10 divisions. We'll see what that looks like. 10 here for the U, 10 here for the V, and looks like we've got some divisions in there. And the output is going to be a mesh, which I'm going to preview using mesh edges. Mesh edges now show all the edges on our mesh. So it looks pretty good, actually. So I'm going to turn this off so we can just see the wireframe. Looks kind of like a Christmas tree. So there's a few things that we want to do to be able to turn this into a structural analysis model, or just a rational structural model in general. One being that we have a lot of overlapping lines here. Right now I'm going to separate out the different kinds of lines. Okay. So we've got the naked edges, the ones around the outside, and then we've got the interior edges. So what I'd like to do is to separate out the vertical elements from the horizontal elements. And since we can think of the lines as vectors, I will be turning those into vectors and then performing a dot product to be able to determine which direction they're going in. And let's see. So what we'll need is a unit vector. So for this one, I've got a unit vector here. I am going to dot that with a z vector. So these are lines going both vertical and horizontal. So if I dot it with the z vector, then what I want is, I think, going to be, let's see, these are all negative values. So the dot product is going to be zero if it's perpendicular to the other vector, and it's going to be 1 if it's parallel to the vector. So all the things that are equal to 0, I'm just going to check this first, and I'm going to use, so that's an equality component, use a sift pattern, and then I'm going to use that as the pattern. And let's see what we get. Oh, I need to put a 0 in here. All right, so let's see what we've got out. So we've got a line here. Oh, look at that. So these are the things that are not equal to 0. These are the lines that are equal to 0 because they are perpendicular to the z vector. So now we've got a simple way to separate our geometry out. I could make different assignments to those down the line when I want to start assigning properties for the structure. So what I'd like to do is going to separate out the ones that are the very top, because I think in reality, this joint at the very top would be very difficult to figure out. It'd be a lot of miters and at the end of a piece of wood, and I think that joint is pretty complex. It's got 10 members all framing into it. So I think what I'm going to do is I'm going to filter out those ones that are at the top. And the way that I'm going to do that is I'm going to first, this is going to have some nulls in it, so I need to clean the tree. Now I have some clean data. And what I'm going to do is I'm going to look at the endpoints of the lines. And let's see, just double checking which orientation this is in. So it looks like the ones up on the top are the start and the ones on the bottom are the ends. So what I could do is deconstruct this point to get the z values. And I know that the z values at the top are going to be equal to the total length of my cone. So what I'm going to do here is another equality check. So we're going to check those z values with the length that I've input. And that will be passed into another sift component. And the pattern being whatever is equal to that z value, I'm going to actually remove. So all of these points at the start, I'm going to filter those in. And then when I look at the end, let's see. So these are the ones that are not equal to that height. Now, since those came from the lines originally, what I actually want to do is just get the lines out, because I don't care about the points necessarily at this point. I just care about the lines so that I can get assign those as structural members. So I'm going to turn some of this stuff off. There's a lot of stuff going on here. So you can see now we've just got our lines. Oh, there's something interesting going on there. Interesting. Right. All right. So now I've got all of these, and now turn those into structural objects. So additionally, let's see, I don't think I need to do anything with this right now. Let's see, these ones are going to be at the base. So actually, I think what I want to do is I want to turn the ones at the bottom into to restraints for a structural model. So I'm going to use this same process here. Not for these though. I'm going to take these points and I'm going to make them equal to 0 since the bottom of my structure is at 0. And then what I should be able to get out is the points at the bottom, which are equal to 0. So now I've got some restraints. And I notice here that that I've actually got a line here for a naked edge, which I probably should merge in at the beginning. So what I'd like to do here is should just add this to the existing ones. Now, I think that naked edge might be 2 lines. So I'm gonna give this a shot here. What I need to do is the same process here, filter those out using the vector and using the existing line. And let's see, let's hope, yep. So I've got this out. I think some of those might be coincident. So I'm gonna calculate the center of those polygons. And now I'm gonna get all of those points. There's a called duplicates. So I'm gonna take the duplicates. I'm gonna leave one. So that's gonna give me just the points that are left and the indices of the points that were left. And what this means is I can go back to that original line. And since I had, let's see, I got 30 lines here. So I know that that's definitely not the right number of lines. Since I get 10 after I cull them. And so what I need to do is do another sift, or no, actually do a list item. So I'm going to feed in the lines and the indices for the ones that are remaining. And what I'm getting out are the lines from that. So I'm going to merge those in here with the rest of these and flatten them so that I get what was the same. And now when I'm going back to everything downstream, I should see that I've got the points that I want, and I've got the lines that I want. And now I can start turning some stuff off. I just want to see what those lines look like. Oh, and here it looks like this might have actually been, oh, yeah, left on. Okay, so now we've got our lines, we've got our restraints, so we've got our verticals, we've got our restraint points. Now we just need that ring. Now the ring is going to be the other side here. Right now I'm going to move my graph down because I like to stay within the boundaries. So I've got my ring here. And now this is a series of lines that also needs to be cleaned up. So what I've got is a bunch of lines that are a ring around the tree. And now let's just test this out. We've got all of our stuff here. Move this up so we know we've got our different objects, got restraints. Move this up here so I know that these are both lines that are going to be assigned to frame members. And here are the restraints at the bottom. Cool. So let's look at that. Nice wireframe model. Could be a Christmas tree. Could hang some stuff off of that. I'm going to play around with this. So this is the geometry for the radius. This is the height. You can do a squat tree. You can do a tall tree. I'm going to do something to start that's a little bit more realistic. So I imagine that 1,000-inch tree is quite big. I'm going to reduce this. So let's play around with how many points we have. Let's just say maybe 6. It's a nice hexagon. Then this number of points, let's see. Kind of want enough that I get a little point at the top. Looks like 8 is probably a good number. This could also be it looks like it could be a tower for like a radio tower or something. So that's actually kind of cool. All right. So now we've got our geometry definition. So that's the first part. Now, next, I'm going to show you how easy it is to create a structural model using Fenix. So first, what I'm going to do is going to grab a model definitions component, which is the first thing. So you can go up here in general. There's a lot of stuff in here that you can change, but model definitions is what every model has to have. You can also just type in model definitions. And that's going to be the first thing that comes up. I like to keep mine up in the corner so I know where it is at all times, because we're going to click on this define button quite a bit to define our model. So let's see. Just to start, you got different codes that you can put in here. Right now, we're just working with IBC 2018. That's what we've put into the program, and what we've built out for design checks. I won't worry about all this stuff. This is what comes up on calculation reports, but I will put an address. Let's just say I'm in Portland, which might be where I really am. I get a latitude, longitude. That's great. That's going to be useful later. You can see the unit system. which I can modify. I think one of the things I'd like to do, this is for input units. Length is attached to the Rhino model, so it's in inches. If I want to update that, I have to go back to Rhino and modify it. Otherwise, things could get really complicated if your model units are different than your structural analysis units for the input of length when you're modeling. So one thing I know I'm going to have to do is I'm going to put some frame loads on here. So my force per length unit, kip per inch is kind of hard to understand. It's a very small number to get something like 100 pounds per foot. So I'm just going to change this to pounds per foot so that I know that's going to be my input when I start assigning loads. A lot of analysis options here. I could just leave these defaults. That's probably fine. I'm going to change maybe risk category, site soil class for seismic. I'm going to do a little seismic analysis here, which will be fun. This doesn't actually have a lateral system yet, but we're just going to assume that it's going to be maybe a frame system with a, let's see, what do we got? Actually, I think I would rather have a cantilever column system for timber frames because this is going to be wood. So let's do the same thing in both directions. Now what you'll notice is that this will impact what I'm going to do next, which is import some load patterns and load combos. So the patterns can be defined here, but what's easier to do is to define the load combos because those create the patterns for you automatically. So I've got load combination window. I'm just going to go with ASD because that's what is used for wood typically. Not that we can't do LRFD, but for this, I'm just going to do a dead load, then maybe the 1 dead and 0.7 earthquake X and Y directions. So I'm just going to import these three. So you can see they popped up here, all of these different factors that are associated with them. We've got the patterns that got created automatically. We've got the vertical earthquake and the X and Y direction earthquake. If I go in here, I'm going to edit the load pattern to show you how it works. So we've got an auto lateral load, which is per ASC 7, and then different lateral forces. So here, I've got a lateral force that automatically got created based on my site information. So latitude, longitude, which I did earlier. I queried that from my location. And then all this seismic data came in from a query from USGS already. If I query that again, it's not going to do anything because it already did it. The auto seismic base is just the lowest Z. That's fine in this case because I don't have a basement level or anything like that. And then my R factor is 1.5, which is for the cantilever timber frame. So all this stuff was automatically done for me, which is really nice. So now that I've got that, I'm going to grab, let's see, what else do I need? A lot of materials come in already. I'm just going to pull in some frame sections. In this case, I'm going to use some wood sections. So from here, I'm just going to get the shapes that I think that will be required for the analysis. I'm going to get a wide range of stuff. So right now, I'm just going to start bringing in anything up to maybe a 12-inch section. So I'm just going to go through here and assign these. So I've got 5, got 6 1/4 by 13 1/2. Let's keep going. We've got 8 3/4 by 13 1/2. And then we've got, let's see, 10 3/4 by 13 1/2. And then one more, 12 1/4 by, say, 13 1/2. All right, I think that is probably a good place to start. So I'm going to save and close my settings. Now I've got some settings that I can work off of. Now, the actual creation of the model is fairly straightforward. So what I'm going to need is I'm going to need some frame elements. So we call those design frame element. So I create a design frame element. This is going to take the lines, and it's going to take the loads that I have. So just for fun, I'm going to start with, I'm going to do separate ones because I think that will be useful. And I've realized here that I have a null in here after I did that. So I need to clean my tree again. All of these sift patterns create these nulls, which can be problems. So now I've got that. This is asking for cross sections. So nothing has been defined yet inside of the component. All these components, most of them have these buttons that you can click. These nice frames pop up. So I'm going to look for my cross section that I just put into the model. So I can put any one. I'm going to start with the smallest one. I'm going to let it do its section rotation by itself. So we'll leave it at default, center line. I'm going to go to glue lam. A lot of materials to choose from. I'm just going to say it's maybe a better, higher quality, higher grade glue lam here. And then the rest of this I'll probably leave. Let's see, maybe I want to mesh differently, but we'll see what it looks like after that. I'm not going to release anything right now. For the verticals, I think I'm just going to do a cantilever. I'm just going to assume that they're going to have some sort of moment connection to the base, which who knows what that details looks like, but that'll make this this demo a little bit more straightforward. So these ones are going to be columns, and I think the rest of this stuff, I might want to do some design automation. So I'm going to click Automate Design. There's some options in here for some different things. So we've got a deflection check for deflection limits, and we got strength checks. I'm going to turn off deflection checks because this might not be a deflection governed design because it's kind of like a structural sculpture out here in space. And I'm just going to add all of the sections that are, these are the sections that will be considered for the automated design. So we've got all that stuff in there. I'm going to hit OK. I'm going to make a copy of that because I think these rings will also want to be similar things. So I'm going to leave all these options the same. I think I'm going to call these beams. That just matters for some of the checks that get performed. I'm going to release the ends. These are the end moment releases, and then maybe one torsional release. And we'll just assume that these are like braces in between the cantilevered columns around the perimeter. And so we've got 2 frame definitions now, and we've got restraints. So we need a design point. So I'm create design point element. This is going to take the restraints. Oh, this is another one. I forgot to clean the tree. Speaking of trees, here we go. Got another clean tree. I'm going to turn these off. Okay. So now we've got a point going into our design point element. Restraints, you just click through. These do recreate the object every time. So if you have this plugged into a live analysis, it will be updating every time you click those buttons. Something to be aware of. Yeah, and the last thing here is we need a load for these lines. Right now, they don't even have a dead load assigned, so they are weightless. So what I'd like to do is create a frame load. So design frame load here. There's a few different ones I could do for frames, but a line load is pretty straightforward. I only have a dead load option, so that's what pops up when I click on that. Because I'm not assigning the earthquake forces are auto, so I can't assign those. I could do a static earthquake force, but then I'd have to go back and define my load patterns, or add that to the load patterns before I can define it. So here we're in the global coordinate system. So these loads are going to be assigned to the global. Z is up. So I think what I'm going to do is let's just start with maybe 10. Remember, I changed the units, so it's pounds per linear foot. And I'm going to make that negative. I can get to it. So this is going to be -10. So negative Z direction is the applied force, start and end magnitudes. And now I just have to filter those in. So this is both assigning an additional dead load, plus if I were to make this 0, it would be self-weight. So now we've got pretty much everything we need to create a model. So let's create a model. So we call these generic design models because they're generic structures. They're not really related to a building shape necessarily. They're just sort of a general structural model for analysis. So I'm going to add these in here, and sometimes the data structures get messed up. So I'm gonna make sure this gets flattened. Okay, cool. And right now it's running validation. validation probably isn't necessary on this, but this would check if the geometry is too close to create a mesh, or if there's any meshing errors, they'll come through here. So this is validate input for the geometry that's coming through. And if two members are not quite touching, it'll throw some errors. And then for the model validation, it's going to throw errors if maybe the mesh is too small in some areas after it does some auto meshing. Right now, we'll just leave it off because we don't actually need it, because this is such a simple model. Now, we're going to run analysis. So we're going to analyze our model. This is just a single analysis, so I'm going to pass the model into the analysis. I'm going to add a toggle for running the analysis. So what I need to do here is check the load combinations that I want to include. I'm going to include both the seismic. In order to actually get the seismic forces out for an auto ELF, I need to run a modal analysis. So that's here. Modal options are the second one. So I'm going to run modal. I'm going to run 10 modes. I'm going to include the dead load, the factor of 1, so that I'm including the dead load as the mass, which is what you typically do. I'm going to hit OK. So now we've got a model out. And looks like I've got something. So so right now I can go through and preview the model. Oh, it looks like maybe something didn't analyze properly. Oh yes, I haven't checked the toggle yet. So right now I can view the properties of the members. So I can see what the sections that were assigned. I can extrude these to show an extruded shape. Click auto because the extrusion sometimes takes long for big models. So yeah, looks pretty good. Got a little timber structure there now. Those are all drawn in the center line as well. Okay, great. And the materials, I can see lots of other properties too if I want. Let's see, let's check to make sure that I've got the loads applied properly. Looks like negative 10 pounds per foot. The settings will pop out so that I can change some of the scales of these things so I can see them a little bit better. 10 pounds per foot is not very much, so I need to scale that up quite a bit to see it. But you can see, got arrows pointing down. Same thing for all these frame elements. They also have these arrows pointing down. So we've actually got all of our loads assigned properly. So that's good. Now I'm going to turn this off and actually run the analysis. So let's see what happens. Oh, looks like it's done in about a little less than half a second. So that's good performance there. So now what I can do is I can look at displacements, forces, stresses, if there are any. This is for areas, displacements for nodes and frames and shell elements. Let's see what that looks like right now. So it's not too bad, but this is pretty much a structure made up of columns, so not too surprising that there's not a lot of vertical displacement here, just in the braces that are taking on some load. But let's change the load combination to one of the earthquake. Oh, there we go. So we've got display shape here from that load combination, and you can see that it's deflecting quite a bit in the X direction. Quite a bit, actually, 168 inches. So what I could do here is while I'm looking at the display shape, I can go back in here, I can look at my vertical members, and let's just manually change those to something much larger. Let's just see what happens. Oh, that's much better. Okay, so we've got a live preview of what's happening. I can show the display shape. So now I'm only 5 inches deflected. That's actually not too bad over the height of this structure. So just for fun, I'm going to switch it back to where it was, and then we're going to run some automated design on this. Okay, so to run an automated design, so we have automate design. So this does design checks, and it sizes up components automatically with some pretty simple algorithms to increase the structural area or the section modulus or whatever it is that needs to be increased in order to make the section work. And so it might do that a number of different times. So we have a few options on here, one being the number of iterations. So this is very similar to what happens in this component, just the analyze component. It takes all the properties from that, and then it just runs an iterative analysis that does design checks in the background. Those can be heavy, so we don't actually do that as part of the typical analysis, but you can do design checks separately. If you wanted to run design checks here, we can run those in and we can see what the design is. So here we've probably, the top elements aren't doing too bad. But if we look at the DCRs, we've got a DCR of 9 down at the bottom. That's probably not going to work. This structure is going to fall over. So we definitely want to run that automated design. And the way we do that is we run it through this iterative analysis. And I'm just going to say maybe 5 iterations maximum. So it will stop after it converges. So it may not actually run 5 iterations. It just depends on how long it takes to converge, and it might not converge, which is why we have to set a limit to it. So here we've got now the model that gets passed out. And let's see what it came up with. So we've got our sections here, which I'm going to now extrude so that we can just visualize those. And it looks like, oh, we've got some interesting things going on here. I think that these are probably getting sized up due to the center of mass being near the middle of the structure. So that's probably being forced by the earthquake forces. So let's see what we can do here. We got sections. So we've got some 12 bys at the bottom, and near the top, we've still got some 3 bys. So it depends on what is taking that lateral force. I think in order to make this a little bit more realistic, what I'm going to do is actually join those vertical elements, since I am making them into cantilever moment frames. And so all I'm going to do is join the curves. Once I join them, I'm going to have fewer number of curves. So I've got 42 here versus the 6 that are coming out. So I'm just going to switch that out live. So now you can see that I've got a single member that looks a lot better, which are 8x13s, 10x13s. And this is, I think, mostly due to the orthogonality of the way that the forces are distributed based on the earthquake forces in the X and Y directions. So because of the way this is shaped. So we've got those. I'm going to show this by the DCR so you can see which ones are getting hammered and which ones aren't. So the ones in the X direction are, I think, probably taking more load in their weak axis, and that's why that they're getting sized up more. But we can play around with it and see what's really going on. All right, so I'm going to turn these sections off, but we can see them grow or shrink. Let's see. Let's show that displaced shape again. Let's see where we're at. We're at 8 inches, which is not too bad. Let's go over and see. What was I at? 591. So that's what's that? A little over 1.5%, something like that. That's actually a decent drift. So so this, this might actually be a structure you could put up. But don't quote me on that. I have not endorsed it. Let's see. What else can we do here? All right, so we've got our iterative analysis. Yeah, since this is all completing in about a half of a second, I think what I'm going to do is I'm going to play around with some options here. I guess one thing, yeah, this is actually pretty cool to see, which is the modal analysis. If you're wondering what the mode shapes look like, up the displacement scale quite a bit. Oh, and this is actually kind of interesting. I think it might be an effect of the geometry, but we've actually got a torsional mode as our first one, which is probably not ideal. So I think we either need to make this more of a slender structure or do something else. So we got the third mode, it's the primary X. And then where do we got the, let's see. Yeah, there we go. So the second mode is in the Y direction, and then the third mode is in the X direction. But the first mode being torsional is not usually a good sign. So what we're going to do is we're going to go back. We're going to modify the structure a bit, and we're just going to do this live. And let's look at the DCRs while we do it, because that'll make for a nice preview of how the structural shape and the section sizes are changing. So I could slide these, but it's going to be half a second, so it's going to be a little laggy, but let's just see what happens here. So if I make this 7, great, 8, great. Okay, those are looking much better. They're yellow, so they're not being, they have a lower utilization. Let's try maybe a different length. So let's go up a bit. Ooh, okay, wow, that's a pretty steep one. All right, here we go. All right, so this is more symmetric. So now we're actually getting members across that are looking like they're stressed the same. Probably shouldn't have picked something that wasn't going to be symmetric to begin with. But this actually looks like a decent design. I wonder if I go down to, let's see. Yeah, I think I have to go at least 8 here. And then for the rings, I might actually reduce those. This is also going to reduce the total load, so maybe I'll increase that. So let's go to 4, and then I'm going to actually split this out so that it's all fair in the analysis. So the vertical ones are still going to get 10. Let's see. Yep. And then I'm going to up this to 20 to get a similar load for the rings. And this is going to be applied down here. All right, let's make it to be a fair total load being applied. All right, so it actually looks kind of good. Let's see. Yeah. Okay. Let's see what else we can do. This is a pretty tall one. Maybe let's try to make it more of a Christmas tree shape. Let's make it a little bit taller. All right. Might have maxed out our sections there. So let's look at the sections. So 12 by 13. And if I look at the DCR that's associated with that, let's see what we've got. 1. Okay, so this is stressed to its max. This is the tallest tree that we can get with those sort of 12 by 12 members. So let's call this a good tree. The last thing that we can do is I want to preview, let's just say this one here. So we have design reports. I can pick one of these objects that was selected. So I have to select the Grasshopper object. And here I get a nice report. I'm actually going to move this to the side before I do that so I can see both at the same time. And let's look at the report. So the report shows that we've got, let's see, a little bit of shear. There's our moment. It is a cantilever frame, so that makes sense. Let's see, here's our, yep, there's our EX, EY. So we've got a moment diagram. You can see the moment at the base is going to be highest, and then it's going to shrink as it goes up. So the highest moment is at the bottom. Yeah, it's important to note the orientation of these since the start of the member was at the top and the end is at the bottom. Gotta maybe flip those if we want a moment diagram that looks more rational. But we have axial loads. These all look realistic. We got our rings where we got some increases in axial load as we go down. And then we've got our utilization checks. So what I think I'd want to get at is, so we've got everything total. Dead load's not doing much. The EX, EY are actually doing a very similar thing. Of course, this is one that's sort of 45 if you're looking in plan view, sort of a 45-degree angle. So it's going to get equal EX and EY loads. So it actually makes sense that these are going to come out the same because it's the same force in the X and Y direction. But let's just see. So we've got, let's see, buckling checks, bending DCR. So yeah, this looks like the controlling case. So we've got a decent amount of stress in the primary axis and the secondary axis. And then we have a 0.916 DCR. And if I wanted to print this out, I could. Let's save it as a PDF or just print it. And we can review that and send it to somebody else to review, so that we can do our full structural analysis and structural engineering work. All right. So that is pretty much everything that you'd need to know to create a Christmas tree model and to run structural analysis parametrically through Fenix and Grasshopper.